just that. Because we are a member of this Clean HME project, and in this project, as an industrial man from the past, I am in charge to have a look at what we could do with such a beautiful energy source. And this afternoon, I'm going to focus on making hydrogen, because, you know, hydrogen is going to be a major vector for energy transportation. I don't know if you are aware of that, but hydrogen is already largely produced in the world. 70 million tons of hydrogen every year. This corresponds to an energy content of 330 million tons oil equivalent. This is more than the primary energy consumption of Germany. So it's not a little. And you don't see hydrogen all over the place. Why? Because it is mainly produced in oil refineries, and it is used in oil refineries to make refined oil products, you know. And I can tell you, when you drive, when you operate a refinery, you always look at your hydrogen balance. You know, you must produce enough hydrogen to make everything you want, and not more, because you don't have any consumer for hydrogen except yourself. And this is the reason why, by the way, when a refinery is built up to make some products, you know, it is unable to make a different sort of products. If a refinery set up to produce diesel oil is not exactly made as a refinery designed to make gasoline. These are different products in terms of hydrogen balance. And to make this hydrogen, you make a steam reforming, you know, CH4 with H2O, you can get H2 plus, of course, a lot of carbon dioxide, just 830 million tons of carbon dioxide. This is 5% of worldwide carbon dioxide production. And should these 70 million tons of hydrogen be produced by electrolysis, we would need a lot of electricity, more than all the electricity produced in Europe. So it means that if we want hydrogen, we have to do something, you know. So tomorrow, hydrogen is considered as a major vector. It will increase dramatically in the future, and it will be produced mainly by electrolysis. And electrolysis, you need electricity, that's obvious. And in the view of the European Commission, by the way, we are on board the European project, so we have to be at least aware and in line with the views of the European Commission. Hydrogen is a major, let's say, actor to reach this European Green Deal. And this is an incentive to investigate how HME or LENR could be used to produce hydrogen. So, well, let's start things easy with LENR reactors, or hydrogen metal energy reactors, as we call it in this project. You can produce heat. In heat, we know how to convert it into electricity. If you have electricity, it's easy to make, on the paper, hydrogen with water electrolyzers. And here I am going to talk about using this heat to make electricity to drive electrolyzers. No production of hydrogen via chemical routes. It's also possible, but it's a different thing. The fact is that if you operate these electrolyzers at different temperatures, you need different quantities of energy, and this is of electricity, and this is what we are going to see soon. So there are several types of electrolyzers. Everybody in this room knows what an electrolyzer is, so I don't want to spend time on this. Alkaline type with potassium hydroxide mainly. And okay, you get hydrogen on one side and oxygen on the other side. Proton exchange membrane. This is a different setup as image here. And also solid oxide electrolyzer cell. And to make a long story short, let's say that these different electrolyzers work at different temperature levels, you know. Alkaline, this is up to 100 degrees C, a little bit more if you wish. Proton exchange membrane, you are limited by the membrane at quite reasonable temperature. And with solid oxide electrolysis cell, this is the contrary. You need a minimum temperature in order to have this zirconium oxide membrane made conductive of electricity. At low temperature, this is the perfect insulator, and you need to reach a minimum temperature in order to have this electricity flowing through. The fact is that typical cell voltage is lower because of this high temperature, and also thanks to this high temperature, you don't need catalyst. In these alkaline or PM electrolyzers, you need a little bit of palladium, platinum, iridium, and you have it, cobalt, rare metals for this 21st century. We have to make sure that what we are doing will not exhaust the planet in terms of rare metals. So let's go back to thermodynamics. H2O can give you H2 plus oxygen. The enthalpy of the reaction is just this, and if you divide by the Faraday quantity of electricity, you get 1.48 volt at 25 degrees C. That's well known. But if instead of delta H, you look at the free energy delta G, it's less, and this equilibrium, I'm going to correct that. Voltage is just 1.23 volts at 25 degrees C. So, and these voltage levels depend largely on the temperature, because this enthalpy or free energy for the reaction vary with the temperature. First thing is that hydrogen is a gas, oxygen is a gas, water is a liquid. So according to the primary principle of thermodynamics, the first thing you have to consider is to transform this water into a gas. If you are operating below, let's say, 100 degrees C. Above 100 degrees C, the water is no longer water, this is steam, depending on the pressure, okay? And then you transform a gas into two gases. So this is the reason why when you raise the temperature above this level, you already get the economy of this evaporation enthalpy. Now, the higher the temperature, the more energy you need altogether, but the less electricity you need. And this is the whole point. It's easy to make these calculations in an Excel sheet, and you get this voltage, you know, what we call the thermal neutral voltage or adiabatic cell. You put electricity in an adiabatic cell, and according to the temperature, you need this voltage. And if you cut the current, you interrupt the current and you check the open cell voltage. Immediately you get this voltage, you know, because this electrolyzer can also be a battery, fuel cell. And the higher the temperature, the lower this voltage is. In the literature, And in the industry, you know, all electrolyzers operating at different temperatures follow more or less this curve. You know, this is an easy curve to fit the different points you find in the literature from different sources. But it's for sure above 650 degrees C. Yes, some people pretend do electrolysis at less than 1.3 volt. So it means that in terms of thermodynamics, if you want to split this water below this temperature, you produce some heat. You consume electricity, you get hydrogen and oxygen, but you have also heat losses. And above this temperature, you need electricity, but you have to inject some heat to have this electrolyzer going on. You know, in other words, in a low temperature electrolyzer, you put electricity, you consume electricity, and you get hydrogen and oxygen, and you get conversion losses. You know, in a high temperature electrolyzer, you inject electricity. You have to pour as well some high temperature heat, and you get hot hydrogen. It's important. It's hot. It's nice. So then it's easy to imagine something like this. You have a high temperature hydrogen metal energy reactor giving you some heat at high temperature. You have here a conventional generator, you know, steam turbine, Stirling engine, whatever you want. To get some electricity. By the way, you may need part of this electricity to drive via some excitation this reactor. We should not forget it. And this electricity, you can use it, or you can for export, or you can use it also in this high temperature electrolyzer. So I made a very simplified model, you know, considering just this high temperature reactor, giving you some heat in the generator and more heat in this electrolyzer. All the electricity goes to the electrolyzer, okay, to get hot hydrogen. And these are the results, no, not yet. In terms of efficiency, to convert this heat into electricity, I just put an easy number. The electrical generator efficiency is just 3/4 of Carnot efficiency. You know that this Carnot efficiency depends on this hot source temperature, and you get something, you multiply by 0.75, and this is what I use in this calculation. And you get this, how much hydrogen we can get per megajoule of heat produced by this high temperature reactor. And the higher the temperature is, the more hydrogen you get. So cubic meter of hydrogen per megajoule of heat. Well, we could convert this quantity of hydrogen into chemical energy containing this hydrogen, and this is what you get. This is the curve showing what you would get in terms of electricity should you use all the heat to drive only this electrical generator. Okay. Now, if you use all this electricity to produce some hydrogen, if you use a low temperature electrolyzer, this is what you get. And if you use a high temperature electrolyzer, all of a sudden you realize that you produce more chemical energy than your electrical generator is giving electricity. Of course, the difference is coming from heat put directly into this high temperature electrolyzer. Also, it's worth to remember that this is hot hydrogen, and because it is hot, indeed, you have all these sensible heat of this hydrogen and oxygen mix. When I say chemical energy content, the energy efficiency is obtained by the ratio between the chemical energy content of hydrogen produced in the previous slide to divided by this heat input, considering that you can divide, you can define two efficiencies. The high energy values, this is of hydrogen. The hydrogen high energy value is 3.5 kilowatt-hour per cubic meter. It supposes that you can you take into account the condensation of the steam into water. And the low energy value, this is just 3 kilowatt-hour when the steam is not condensed, you know. This is basically the same thing. If you have a high temperature electrolyzer or a low temperature electrolyzer, the energy efficiencies are quite different. So it shows that it's worth to consider the advantage of high temperature LENR reactors, you know, if you are thinking about hydrogen production. Again, this system delivers hydrogen at high temperature, and hot hydrogen can be is used to manufacture chemical products already today. For example, in some refineries, you can get methane reacting CO2 with hydrogen, you know, to get methane plus H2O. You can produce methanol also, you know, like this. You can produce synthetic liquid fuels via the Fischer-Tropsch reaction. The first one, methane, this is the Sabatier reaction. And, but you have also the possibility to produce ammonia directly with air and hydrogen. Or, for example, just to give you another example, maybe outside your daily way of thinking, metals like iron and many more. This is a picture obtained from a paper in Science, you know, you get methane, you get methanol, you get ammonia, but it's possible. And here you can get iron. You know that if you want to produce iron from iron ore, you use iron ore and coal. But anyway, in a blast furnace, you produce a lot of iron and a lot of CO2. But in some countries where this natural gas is cheap, this natural gas is used to produce hydrogen. Yeah, again, methane steam reforming. And this hydrogen in use in some furnaces, for example, from this company, LENR, this is the leader in this field, sorry, to produce what they call direct reduced iron. So we don't go through hot metal pig iron into oxygen converters, they get directly this iron. And considering the need to avoid the use of natural gas and production of CO2, you know, they develop, for example, a system here. This is just a concept with an electrolyzer making hydrogen, cold. So you have to heat it to go into this shaft furnace to reduce this iron ore. In our case, we will directly produce hot hydrogen. So we can replace these two steps by what I presented a few minutes ago. So in terms of conclusions, this hydrogen metal energy reactors working at high temperature can be used to generate hydrogen with high temperature electrolyzers, you know. For the present time, this is solid oxide electrolyzer cells. And this hydrogen is delivered hot and can be used directly hot to make many different kinds of products. That's all. Thank you. No question. Ah, thank you.
Couldn't figure out what the gain energy you get. What gain energy do you get? You said that to do the same thing, you need all of the electrical energy in Europe. Do you get half of that or more than half of that? Do you think?
After such a good lunch, I'm not sure to understand you.
You said, slide number X. That you will need all the electricity of Europe.
Yes.
To do that.
This is the chemical content of this
If
hydrogen.
you work at 800 centigrade, how much do you need?
Ah, you would need less.
Yeah,
I guess this is, frankly speaking, the normal electrolyzers, you know,
yeah,
and like this one.
right.
This is the typical industrial electrolyzer. This one, this is an alkaline electrolyzer operated at 1.5 volts or something like that, maybe more. And by the way, Arnaud, this is in Belgium, this one, for a project to produce hydrogen, to combine it with CO2 to get some methane. So this is already in the pipeline, you know, using electricity to reduce, to avoid production of CO2 and even to capture some CO2 to make useful products, you know. Of course, but you don't add CO2 to the atmosphere. You recycle your CO2. It's already something. It's a different political theme to say we will capture this CO2 and sequester it, you know, store it on the ground forever to reduce the amount of CO2 in the atmosphere. I'm not going that far, but some are doing this. Maybe it will be the speech at the end of this century, but Johnson will see.
I'm glad you mentioned the political dimensions of hydrogen, many of you know. I'm on the edge of the hydrogen business myself, and with electrolysis as a system, there are some big logistical, practical problems that governments have not yet acknowledged. But there are also practical and production problems. For example, there are many, many holes in the food supply network where maybe for 100 kilometers in any direction, you could not put a 2 or 3 megawatt electrolyzer to produce hydrogen because there simply is not the electrical capacity available or the cables available.
Yes.
And a lot of people don't know that in the UK, for example, if you want to install a 2 megawatt electrolyzer, then the minimum charge for connecting it to a very close grid supply will be of the order of €200,000. Plus, they will charge you around about 10% of that figure every year for insurance and maintenance of the connection. Then, on top of that, you have to pay, and the energy costs are enormous, you know, but that's another story. But the second problem that exists at the moment is there's more interest now in solid oxide fuel cells, but the underlying reason for that is not so much that they are very much more efficient than membrane fuel cells, is that there is a worldwide shortage of membranes. And there is insufficient, they're monopolymer, I think they've got monopolymer material, and there is not sufficient production capacity now. And I think lead times are now stretching out to almost 12 months if you want to build an electrolyzer. You have to put your order in a year before you want to membrane. While we're talking about membranes, I just mentioned that the life is limited. Currently, it seems to be about 5 years if you have an electrolyzer running continuously. And the replacement cost, change the membranes when they fail, is 50% of the cost of the
Sure.
electrolyzer. It's the maddest scheme you can imagine. But we don't have a better one.
This is the situation today. And of course, this is a pig and chicken and egg problem, you know. If we want to go there, we have to solve everything you said, starting with financial engineering, by the way, because of course, having charges for finances and insurances and things like that is part of the problem, you know. This is a major reason why renewable energies were so slow to start up a few years ago. And now it's blooming all over the place because most of these problems have been solved. And with hydrogen, you will, young lady and people, you will see this change as well. How long it is going to take? For the moment, there is no market for hydrogen outside refineries. This is why bother about producing membranes for electrolysers if you don't need them. If for political reasons we need, how much said the Commission? They were talking about 40 gigawatts of electrolysers by 2030. Is that a number for you? It's just 8 years from now. How do you make 40 gigawatt of electrolyzers? You know? We are not talking 1 megawatt. Huh? This is the political push of this European Commission.
That's right, and the UK government just at least in America, the situation is very evolving state to state at the moment, like state concern. But as the federal government in America becomes more interested, they will probably begin to adopt the same policy.
What? So this is the reason why I prefer thermodynamics, you know.
Absolutely. Thank you very much for your time.
Thank you.
Can I ask you a question? You have a question, okay?
Yes, please.
I have a question. When I understood you said even in the case of high temperature electrolysis, you can reduce, let's say, 50% of efficiency compared to the low temperature facility. Okay, it is still a large amount of energy you need to produce hydrogen. Yeah, so if you compare low energy electricity by it's still only a factor that we can win. The problem is, yeah, you said before that we need a lot of amount of energy to produce hydrogen. And this is something important because of renewable energy sources, because of storage to store electricity and so. This is something what is maybe not, or this is another point is transportation, because we think that hydrogen can be a solution for cars and so as a fuel. The point is there is competition between batteries and hydrogen cars. Okay, but maybe the solution is much simpler. There's something what we have discussed today in the morning. We are speaking about the facilities that can produce directly voltage. Now,
we have an electric source, let's say, with reactions, then produce ionize the medium. We have free electrons. We can connect the electrons at the electrode, and then we have the voltage. So we use hydrogen only as a fuel for our nuclear reactions or chemical reactions. Maybe so important. And then we produce directly the voltage that can be used for transportation for all the things. And then the wind and the efficiency will be much larger.
Of course, if you can produce directly electricity, it's a different usage. It's nice.
We talking about, this also very nice example for that. This rocket engines based on the radioactive sources. So the people put radioactive sources, alpha sources that decay and they produce fast alpha particles that ionize the medium.
Do they intend to take off with this rocket from the ground?
No. There is something what you can use in cosmos.
Of course, but not from ground.
No, because you don't need so much of the power to accelerate the rocket.
Sure. But again, we are not in deep space. We are just, in hard things. And I wanted to talk about hydrogen. So of course, we could talk. We hope, all of us, that next time we will talk about direct electricity production. Of course, it will be nice. It will be a different speech. And that's all.
Thanks.
I am sure that George is going to tell us about this more.
Applause.
I just cannot go by city. I have to go to see or taste directly. So I'm going to talk something really heresy. But this meeting is about heresy. It's about the design and operation of let's say ancient or older technical inventions which I would like So most people ignore, but there are a number of forgotten inventions. In my previous talks, I was talking about Nikola Tesla. It's more than an urban legend. There were several witnesses, but he himself never led us any patent or technical description. However, I dug up something very smoking gun. So we shall see what Tesla really did in the 1890s, and then after we have the Moray device, lots of them are witnesses, photographs, and so on. Next is a Hungarian inventor, Joseph inner gas motors, and I shall show you some photographs about this really fast submarine. And another Hungarian water car inventions, Stephen Horvath, working in Australia, and I have some personal stories as well, and at least 50 different inventors who claimed, and in my opinion, did invent cars running nothing but fuel water. Next slide. So actually, this is, I have found some 90 photographs from Tesla when he was actually on court for the priority of radio. And in his affidavits, he left us 90 photographs of his tubes, gas discharge tubes. But there is a very logical step-by-step process how to improve the efficiency of these gas discharge tubes. And actually, he followed the same path as later inventors. We shall see that always somehow sparks are behind of these inventions. So spark discharge is to be the culprit behind all these anomalous behaviors. These are the carbon button, small one, big one. Then after he made a copper belt around it, very interesting geometries of the discharge tubes moving it. And then after we shall have the cones, which were reinvented several times by completely different inventors, completely different times. And one interesting, very important feature, they never talk to each other, never read each other's patent, never read the papers. This is actually the culture of silence, the culture of complete amnesia. And this is what I would like to talk about. And this is the last Tesla tube when he had a rotating discharge, starting from down and then after went up and up and up. So we have rotating particles, electrons here, and this has a central role in this whole story. Next one. So this is the book title of Henry Morey, who had only one picture of his electricity producing device, and actually this is the box, and out of it came the best version is 50 kilowatts of electricity, and it was completely cold. But at the beginning, it was only 5 to 10 kilowatts, not more. And this is notorious Joseph Pop. Actually, this is one of his so-called inner gas engines, but in these engines there were always sparks, and sparks. The LENR community never refers to his work, so he is an alien use. But I think his heritage is very important. We shall see later why. Next one, please. Actually, he invented his device in Hungary in 1957, just after the revolution. This is a jet propulsion LENR submarine, and it has a very unusual construction. Here is the, let's say, the pilot, and the core of this submarine is over here. It is heated to white hot temperature, and he was able to reach 300 miles per hour, and he crossed nearly completely the Atlantic Ocean, starting from Canada, and within half a day, he nearly reached the French coast, and then after the machine failed, the submarine sunk and nearly killed him. Actually, he survived just barely. In his book, he described the story, but he never revealed the technology behind it. However, in his patents actually so we can make a reverse engineering. So actually, it is always the same stuff next to it. This is the biggest LENR reactor in the history. This device, this is a ramjet, like the FAU1, the same principle. You have a small explosion, and with the help of this explosion, you kick out, let's say, a couple of liters of water at once. So it's kind of a rocket engine. And for this reason, you don't need a propeller, but always like a FAU1 engine, it just picks out always a certain amount of water. And because the cone of this submarine is white hot, there is a very small layer of water vapor, and this whole machine is just flying like in the air. So this is the reason it was able to reach 300 miles per hour. And his wife is here. The name is Tita, Pussy, it means paper cat. And it is there on all these later photographs. Okay, next slide, please. This is the rear of this submarine. This is where water was sucked in at the front, and it was squeezed out at the rear. And this was the simple rocket principle. And this is one picture about when it was sinking into the water and flying the light and airplane beating the water. Actually, he was an ardent nationalistic Hungary. This is you have this inscription next, please. Next slide. So, in my opinion, this is personal opinion, LENR is much bigger than you guys believe here. And there are much more type of physical phenomena than in the textbook, well outside the textbook physics. And this has a proven industrial capability for even for clean electric energy production, with continuous operation, and with a small amount of hydrogen. So this is a renewable. Next, please. There are some known types of LENR, like the well-known, I mean, here well-known, palladium, deuterium, low temperature devices. This is what usually discussed here in these meetings. And then after higher temperature, nickel hydrogen. But the problem is it has little industrial use. For me, the main lesson which I learned from Professor Carpentier and his team, that this is great diffusion based, and this is together fission and fusion together, very rich area, very rich family of phenomena, still underexplored, but this is based on the cracks on the lattice. And for this very reason, the practical application is limited, but in geophysics, we just cannot understand geophysics without it. I read Professor Carpentier's book, very fascinating, very interesting. I suggest everybody, it's a must. Without it, we will not understand most of the LENR. Next one. The next family is very simple. It is the dust fusion. Everybody can do it at home in the kitchen reliably. This is where I spent some 5 to 10 years of my research. If you have at home a very simple microwave oven, this is the quartz tube on 2 stands. Put here some carbon particles, and the red light will start the start button, and you will have dust fusion with an extremely rich variety of transmutation. Whatever you can imagine is there. Next one, please. So these are some of the inventors which I found after spending some 10 years in the library of Hungary Patent Office. And you may say that these inventors are liars. These inventors are just dreaming of stuff. But then you have to explain how come if they are liars. The pattern is just the same. They are unaware of each other's work. They have no idea what the other food made. So when judging their work, you have to know one thing. I counted that roughly 200 people have been working on gas discharge throughout the human history, 200. But roughly 2 million garage inventors were fucking around the sparks in their kitchen, in their garage. So 2 million inventors, some of them stumbled into interesting stuff. So in my opinion, LENR or cold fusion is more of an engineering problem, because a number of engineers found very special, and I have to emphasize, very special local circumstances that you have this phenomenon that I find nothing. So I won't have time now to talk, for example, about high-end test practica, but they are mechanical devices, mechanical areas. You wouldn't dream of having a mechanical device running from cold fusion, but these devices are running with sparks. Always this running spark comes up. So there is a fourth group which Bob knows a lot more. Actually, this is the almost device with this underwater bubbles and bubble collapse cavitation. But if this cavitation is done with electrolysis, Mr. Omosa and Brown and some other inventors came up, then we have a very unusual gas, brown gas or almost a gas, and Bob will tell you later about the absolutely fascinating, unusual hair-raising effect which happens here. I don't have time now to talk about it, but he will do it instead of next time. These kind of effects, in my opinion, in sparks are related to so-called condensed plasmoids, but each researcher, each inventor has his own ideas, his own terminology. There is no agreement, and maybe they mean the same stuff under the same name, but they use different words. So this is like people are talking and not understanding each other. So I prefer the terminology of condensed plasmoids, but exotic vacuum objects or heavy electrons or other stuff may be the same expression. Maybe there are some difference, I don't know. We ought to talk and argue and measure a lot more. This effect has been invented or discovered at least 4 times. And actually, this is the oldest by Rudder in the 30s in Hamburg. He made the first photographs about it in a 4-chamber. And it is technically very, very challenging because you have to have the shutter speed of 5 picosecond or whatever it is. So it must be very, very fast photography. Ordinarily, you don't see when these condensed plasmoids are moved. And quite independently of him, Messias in Novosibirsk in the 70s found the same stuff. He termed it as explosive discharges. Explosive, it's another term. But both guys agreed in one very peculiar hair-raising stuff. And later was able to measure the charges in the head, and he even established the charge distribution spectrum, and he claimed that sometimes 1 million or 10 million charges, electric charges, are inside. But none of them ever dared to question how come that so much charge is held together. Then in a uranium nucleus, it is hard to pull together 92 protons, 92 charges. How come that 1 million or 10 million charges are held together? So this big question, which academic research at 205 never dared to ask, but we have to address this question. Next. So everybody in the academic gas discharge area thinks that most discharges are low discharges like avalanche. Then you have a quite even charge distribution. But this is not the case. Whenever we have this large discharge, we have a very distinct negative head. So lots of electrons somehow followed by a positive trail. And it was known by them, by the 30s, that actually the electric field over here is extremely much higher than the overall potential difference. So this huge negative charge with this enhanced field is an ideal place for Coulomb shielding. This is the best environment for Coulomb shielding. You can imagine any pornographic stuff in the field of nuclear science, it is there. So, but you never dare to think, never dare to imagine it is there. The field strength is so intense that anything can happen there. Okay, next one. So, this is the list of so-called academic discoveries, starting with Tesla in his lectures. However, no one in the academic gas discharge research refers to the work of Tesla. It's completely. Then after Turk at the Westinghouse, Pittsburgh in the 30s, discovered these condensed plasmoids forgotten. And then after Rader, Hamburg, then after Nasser, and now comes our age when shoulders, Matsumoto, and some other, lots of Russians, French research. But the thing is that more or less they are unaware of each other's work. These academic researchers are mostly unaware of patents and inventions. They don't care. They don't give a shit. Next one. This is a very simple setup, actually, by Shoulders. You should read his patent. His patents are exceptionally clear and straightforward. And this is only his patents are clear. All the others full of bullshit. But his patents are clear, repeatable. This is how a patent should look like. And actually, he started to use these litmus places to figure out the size of these condensed blood voids, but it was championed by Matsumoto. So Shoulders and Matsumoto were the watershed in this method. These are some reactors for these sparks. Actually, in my opinion, just before Jean-Paul told that he knows personally, he made an excellent work. So give me my regards. So and Korabu team also used sparks, but they were so ignorant about gas discharge that they mixed actually the different regimes. So they wrote in their paper that they are using raw discharge. In fact, they were using spark, but they were so ignorant about plasma physics that if you are an excellent nuclear physicist, it doesn't mean that you have expertise in gas discharge. It's a completely different area. And excellent gas discharge physics know nothing about nuclear physics. Nothing. So these areas which happen in nature hand in hand in the academic world are really continents apart and an ocean in between. So there is no communication. This is actually the pop spark reactor, the first one, actually so simple. There are two, and this is quite unusual, two electrodes in asymmetric manner, and there is a tungsten spiral in between, and you just generate actually with the help of a huge electric pulse, either a melting or just a heating, but anyway, we demonstrated a real comment with this device exploded. It was strictly impossible that you do it on the energy of this of the electric pulse. 100 or million times more energy came out from this drum actually. And in his second patent, already you see this spark gap there is spread around. Next one. And these are actually the Matsumoto experiments. After, let's say, these mechanisms like formation or strange radiation or exotic particles, name as you like, but it looks that they are a collection of magnetic monopoles, solenoid, and so on, because they tend to self-assemble themselves, and even they have these pendants. And sometimes, okay, next one. This is before that hydrogen reactor. Next one. I want this is the ECA type of water car again. Sparks. Next one. This is the gray type of electric generator. Sparks again. And these are our recent results that I don't have time to go. Thank you very much.
So William, volunteer the Martin Weidman Memorial Project, thank you, Dr. Edy, for fascinating talk. And on your chart where you had all the different electrodes, you said you didn't know what shoulders used, well, you used the mercury weighted tungsten tip, so the salt heating, and you shot into xenon with this high mass stabilizer converter and reduce the high yield from efficiently the xenon. Oh, no, you did mention Tesla. In 1932, in his death grade, he also described a tungsten filament technique for mercury. So it wasn't really an original idea by Scholz. But he had an open-ended vacuum tube, and he called it electrical particles of matter. So he was very, very close to understanding the ectons of Messier. And Messier really lost out because he did publish in the West until 1996.
Sure.
So, yeah, publish or be damned.
You haven't mentioned in your talk some specifics that I was in the first research. This research of this chart, self-putting this chart, and then you can get megavolt voltages. So they used already for 50, 60 years. So this is something what is very nice, especially and that's very nice. Of course, the problem is that you have very short start and temperature which are also, let's say, medium degrees or something like this. And if you think about this spark or large amount of plasma emitted for a short time, and you ask about how it is possible to collect positive charges, I think it's possible. It depends only on the time, because the positive forces between the positive charges need time to expand the plasma. If it's very short time, there is no problem. This kind of research is made in the, let's say, iron plate study. If you have fast, heavy ions going through the material, there is a very hot plasma inside, and you have a kind of Coulomb explosion there. So the physics is known. I think there are nothing very special there.
With due respect, I disagree, because inventors were able to come up with inventors like this submarine, and hot fusion physicists are really a worthless bunch of gangsters who are asking more and more money for nothing. And they don't deliver anything, and they want
I agree
to.
with you, but it is something different, because they said we should argue in the same way for the public, to get some public money for research. Okay. And there is no critical element for that.
But these,
Completely different situation.
this is really a Ponzi scheme when you lie to the investors and you ask always for more and more money. And when that money is wasted, you have a bigger lie, and then a much bigger lie. So it's just lies and lies and lies.
Well, thanks. Yes, the postman.
Oh, yeah.
Huh?
The presentation.
I could hardly read that. Yeah.
Could I please colleagues,
It'll be a PowerPoint, yeah.
I can see your presentation. What is the title? What is the title
I can't see it there.
presentation?
It's a PowerPoint.
Okay. And the name is?
Alan Smith.
Ok. Non trovo la presentazione sua. Alan. Oh, no. No.
Well, if you have a problem, I've got it in my pocket.
Ok. Non trovo la sua presentazione.
Non l'ha messo il 30 agosto?
No, non c'è, vedi, non c'è.
Sbagliato data?
No, non c'è niente.
It should be there. I did send it.
Questa.
Questo qui?
Yeah,
Sì.
open.
This one or this one? Ok.
Allora, it's the same, lo stesso.
Yeah.
Mettiamo la data giusta. Questa è la data.
Vai, vai.
Sì.
Sì, no? Sì, giusto.
Mettiamo anche il nome.
Faccio io dopo.
Poi dopo ti dimentichi.
Alla fine.
Basta.
Ok.
Qui. Questi danno. Qui.
Sì.
That's it.
Un momento.
Sì, vai.
Questo è tutto.
Ok.
How do you change the slides?
Allo sblocco.
You can change the slide with the mouse. Okay.
Okay.
Oppure e questo per andare avanti.
Yeah. Oh, down cursor,
Yeah.
up cursor.
Yes.
Okay. Right, I think we're a go. Time short before coffee. So bear that in mind. This is yet another presentation on the direct production of electricity, which seems to be very much flavour of the month, right? Frank Gordon, who has been mentioned by both Jean-Paul and Fabrice David, also contacted me something like a month, 6 weeks ago, and told me, described the lattice energy converter that him and his colleague Harper Whitehouse were working on, and asked me if I could replicate it. So I wasn't sure what it was like, just like Jean-Paul Biberian. I wasn't sure whether I had time, whether it'd be worth it. It looked a bit too simple to me. It just looked too easy. So after a few weeks, I thought about it again, and one of the members in LENR forum, he actually, Antonio Di Stefano, began a very competent replication and started publishing his results in the forum. And Frank wrote to me and said, "Come on, do it." So I did, working with Matt Liddy, who some of you may know. He was here at ICCF 19. Matt's a plasma physicist, trained at Imperial College in London, a very sparkling reputation in the fusion business, and now a convert to LENR. Unfortunately, we've only had about 2 days in the lab to work on this, so these results I must describe as very preliminary. But in my opinion, it looks very real, it looks very interesting, and we will be doing some more work on it. So, yes, obviously, thanks to these guys who let me steal some of their results to talk to you about, including Jean-Paul.
So you're going to get an encore, Jean-Paul. So lattice energy converter stands for lattice energy converter, developed by Frank and Harper Whitehouse, both of whom worked at the US Navy Research Center, SPAWA, and knew some of the, worked alongside people like Stan Spack and so on, and some of the greats from that place, yeah. And it produces DC electrical output. It's not particularly high output. It's not commercially interesting at the moment, but perhaps it has potential. The voltage is actually, although we're only talking at the moment in current iterations of less than 1 volt, probably the best kind of voltages that we'll see at the moment are 700 or 800 millivolts. The problem is not the volts. The problem is going to be, as always, the current, yeah, which at the moment we're talking about microamperes, 1, 2, 3, almost in the noise level, but they are really there. So the best thing about it is its ease of replication. It's, if you don't use palladium, and you don't need to use palladium, the fact that it's very cheap. In one of his emails to me, Frank described how he went to, inspired by the work of Stevenson, of the LNR4, the LENR4, remember, he went to Home Depot and bought a gallon can of toilet cleaning hydrochloric acid and a few bits, some steel pipe fittings or iron pipe fittings, and went home and replicated his own device using those materials. He said, I've got enough material to produce about 100 of these machines, he said, and it cost me $25. There you are, you get some idea of the fact that actually this, if any of you are still in the declining and unfortunate reputation of teaching, will be a great, great advanced student project. To build a lattice energy converter and measure the output, because measuring the output is always where the tricky part is. Measuring electrical output is probably easier than calorimetry, but of course it has its own new family of artifacts and errors that you need to make yourself aware of. So this is the, at the top here, is the design that Antonio Di Stefano, who lives in Sicily and is an electronics engineer, came up with, which, like the devices of Jean-Paul and Frank Gordon and Harper, is a concentric tube-in-tube device, and very simple. Here he used O-rings as spacers to keep the tubes apart. And he's actually filled all the external gaps up with epoxy resin and put a gas valve on the right-hand end as you look at it in that picture. And below there is a diagram, not a diagram, a photograph of a rather beaten up and well-tested, let's say, a very well-tested, almost a distraction lattice energy converter that Frank built with his materials from Home Depot. Those are pipe fittings, and as you can see, yeah, this is Home Depot LENR reactor. So, like any electricity production device, the lattice energy converter has 2 electrodes: a working electrode, as it's called, and a counter electrode. I'm not going to read all the things that are on the screen. It's hardly worth it, but I must point out that it's very unfussy about substrate materials, right? Brass, copper, you know, there's a whole list, mild steel, galvanized steel, a whole list. The key thing is the plating of the working electrode, which Jean-Paul has talked about using palladium because he's comfortable and happy with it and he can get it to work. I've been using iron plating. But there is also, as well as being pretty Catholic about the substrate material, it doesn't appear to make a great deal of difference what electrolyte regime is used as long as it works. I used a Victorian, somewhat modified Victorian recipe for iron plating electrolyte, which was passed on to me by Peter Moberly, who many of you will know because he's a regular attender at these kind of workshops. And Alan Goldwater in America, he's been trying with ferric chloride, I think, and because his background is electronics and of course from etching and so on, circuit board etching, he's very familiar with that kind of material. And Antonio Di Stefano and Frank Gordon have used hydrochloric acid, and I believe Frank Gordon has used some other things as well in his test. So it's not fussy about materials, it's not fussy about the method of electrolysis, it doesn't appear to be, and it doesn't need triggering. When you assemble the device, it self-initiates, it starts up, whether you like it or not. And it seems to be sustained, capable of producing energy over a long period, though I cannot specify what long actually means. It's more than a day, it's more than a week. I've got one at home that's been running now, and I checked this morning, it's still producing a few millivolts, more than it should, yeah. My wife wonders why I keep phoning her up and saying, what's that meter showing? But never mind, she's getting used to that kind of thing. So I have been testing this device, not in hydrogen, but in air. So the only hydrogen in this system is the occluded hydrogen within the metal lattice. So there we go. I think we can skip this one, except once again, I must emphasize it's a low cost and low danger device that requires no exotic materials, which has been replicated at least 4 times. And some of those replicators have, I think, done several dozen or more, several hundred iterations. It is related to the Enterman device that Fabrice talked about. I think that the patentee for the Enterman device in America, they worked together with Frank Gordon and Harper Whitehouse. Maybe Fabrice knows, maybe he's more sure than me. Anyway, here we go. So these are, we talked about materials, by the way. It's also not fussy about geometry particularly. Everybody who's replicated so far has been using concentric tube devices, more or less. And but Matt, Lily and I decided that in the pursuit of more surface area, bigger, faster and flashier, that we would use flat plate, stacked flat plates, almost as in a conventional battery. So we have the picture at the top left there shows plates with just temporary, actually, O-rings, just used as spacers, yeah? And electrolyzed in a 2-litre beaker, and on the top right, you can see a plated electrode. And the iron plating recipe I use, it seems to work reasonably well, by the way. So if you're struggling, I'll pass it on to you, Jean-Paul, if you want to dry iron. At the bottom is the electrolysis setup that Di Stefano used. And his was just using hydrochloric acid, but he uses a bundle of wire or here distributed soft iron wire. I know this is baling wire, the kind of stuff that is used for fence repairs in the countryside and so on. He does live in Sicily, you know. Yeah, he probably got it off a fence. Yeah, but it's also used by welders for holding assemblies together, and it's quite soft iron wire, so a good choice of anode material. And on the right here, you see the 2 components of this cell, the inner and the outer electrodes. The inner electrode is the working electrode here, and the assembled cell in at the bottom center. Not many people seem to know, I certainly didn't know, that iron has a huge capacity for hanging on to hydrogen. It's in this graphic here, which was from a book by Mera. He showed that actually iron is capable of holding more palladium than iron is capable of holding more hydrogen than palladium is, which is rather remarkable. But this gives us a good candidate material, which is inexpensive and readily available, and not a vanishing resource or an expensive resource. Have you seen the price of palladium lately? It's gone up a lot, yeah. And so I feel it's such a good candidate for replication and such a good area to explore. And so that's what we're intending to do, to try and up the output by several orders of magnitude, at which point it will become commercially interesting. And after that, who knows? But Frank Gordon seems very interested in making this happen. He's not a young man like me. I think he's more interested in seeing this happen than he is in actually becoming very rich. But I have the kind of dream that there are, somebody said to me recently, who's in the kerosene lamp business, he said to me, we think there are 1 billion kerosene lamps in the world. And wouldn't it be fantastic if you could replace every kerosene lantern in the world with one that ran on a lattice energy converter or a fusion diode? It would be the most wonderful thing to do, and better for the planet too. As far as how it works, well, Frank Gordon, Upper White House, believe that it may be particle emissions which ionize the gas between the plates. That certainly figures in many ways, but we have not been able to detect any particle emissions from the surface. I had a try with some quite sophisticated pancake Geigers, and even up very, very close to the surface, I could see nothing above background. But there is a paper by Rout and Srinivasan, which I'll quote, it is quoted in the longer paper that I've written and will be submitted to conference, has been, who looked at energetic emissions from palladium hydride, and they found it would fog X-ray film. So it seems that there is particle emission, but not as we know it. So it's maybe very low energy X-rays, of course, difficult to tell. Early days for that. So because of the shortage of time, so I've only had 2 days in the lab working with Matt and a set of prepared electrodes, because they prepare themselves once you set it up. It's a bit like growing tomatoes. You know, you just start it off electrolysing, and a week later you come back and pick it up. We've only had 2 days in the lab. And remember, we're working in air, not hydrogen, and haven't actually got the vacuum system up and running for this yet. So if the plates are separated and then you put them together, right, the output recovers slowly. And interestingly enough, the recovery time in many bears a close relationship to the separation time. Yeah, so if they're separated for an hour, it seems to take about an hour for them to get for the voltage to get back up to the maybe 100, 200 millivolts that you saw in the first place. And if they're separated for a second, there's a table there showing recovery time for output versus time for a pair in air that was separated. They weren't separated actually. We short-circuited the pair of plates with a wire which was itself earthed. So the intention being to drain away all charge to zero, which works very well. And then Matt measured the recovery time and the output. And we had, in this instance, 100 millivolts instantly, which over 3 minutes or so crept up to the 150 millivolts that he'd been seeing before. So it doesn't look like galvanism, though we have had, you know, as I said, it's very preliminary, and we have seen 1 or 2 things that worry me a little bit, but they are not, they're not killer worries. Yeah, I just think we need to be more careful about how this is done, how that is done, and so on. You've got to watch out for humidity and surface moisture on the electrodes. All the obvious things, but nevertheless, when you're measuring voltages and particularly currents, down in the microampere range, you need fairly good equipment, and it does need to be very carefully calibrated. And this is one of the beauties actually of working in a small independent laboratory. Matt and I were talking about a potential artifact which may have been caused by the grid supply, because my building is very near one of the main power supplies to a whole group of buildings. And I said to him, well, I said the best way to answer that question is, this is a battery powered meter. I'll turn off the mains to the building. And he looked at me and he said, can you do that? I said, you just watch me. I said, I don't have to write to a head of department and ask for permission to switch off the power. I can just go do it. So it does help actually. You can move a lot faster. You can move a lot faster that way. So there we are, not galvanism. I cannot rule out entirely some other little known, little understood artifact, and I don't think John Paul would either. I don't think he would. But it looks very promising, does it not? Okay, is it scalable? We don't know. We don't know, but we're going to have a look and see. Okay. There you are. There's some references there. I'll leave it up on the screen if anybody wants to photograph it. And you can also look at LENR Forum. And if you do a search on LENR Forum for Frank Gordon, you'll find a long thread with many, many posts by replicators and so on. Okay, thank you. And you're only 2 minutes late for coffee. Any questions? I'm sorry.
Thank you. I have a small question about the whole experiment. I have a suggestion about how do you define the electromagnetic force produced by any of these reactions?
How do I define it?
It is something to measure a voltage and a current, but do you have any evaluation of the electromagnetic force that is produced by such device? Because what you're doing is you're just either shorting it with a current measurement where you have a shunt, right? Or you're self-collecting the voltage that is produced spontaneously by the serve. But do you have any electromotive force that would be of any use? Because as you may recall, the electromotive force is what actually moves the system forward. So the power that is generated is the electromotive force. Here you just measuring the voltage and the current, so I can evaluate that.
Well, we're talking about microwatts here, yeah, at the moment, very small. But Antonio Di Stefano has done something else, because he, searching for artifacts, looked at the cell resistance, yeah, and so he assembled a cell with blank electrodes, as it were, a control cell with no plating, no hydrogen inclusion, and he measured the resistance in the cell, which was very high, you know, of the order of megohms, because there is no direct electric connection between, there is just a gas phase, a gas barrier. So he did that, and then he tried something else, which was to measure the current flow through the cell with different voltages. So he gave it 60 volts and 55 volts and 50 volts, and he measured conduction, and he got 0 millivolts conduction at those kind of electromotive pressures. Then he actually got an identical system with a working electrode in it and measured the conduction, and he discovered that a working lattice energy converter is conductive. I can't remember the figures exactly, they're in the paper that I've submitted. I got the results from Di Stefano, and it's conductive at virtually all voltages, yeah, and the difference is startling and remarkable, and I thought it was a very good test as well, yeah.
Okay, to all guys that are working on this, I have a suggestion. If you want to characterize better the current, you're measuring, because you're measuring very low values of current. And if you want to evaluate the transition, the transient, any form of current that you're thinking of, it's this little box that is sold by it's the EV blog forum. The guy is very well known into the world of electronics, and he's selling these microcurrent devices. And basically what it does, it converts either nanoamps, microamps, or milliamps into a voltage. It uses this frequently, watch battery, flat battery. And it has a tremendous bandwidth. So if you're looking to evaluate also the transient aspects of the current generated, it might be a very good option. It's very cheap. It's independent, and it produces voltage. So you have a direct conversion of the current into voltage. And I thought that was a good idea to mention that. Today we've been so using all this presentation about this today.
Thank you, Matthew. I'll get the details later.
This is an excellent suggestion. Maybe we should have a source of reference of this knowledge, very important for everybody. To answer this question, if what government did was to measure the voltage for different resistance, and then you extrapolate to infinite resistance, so you get the asymptote. And the voltage voltage is not part of the answer. And now this is a very important question, maybe for Fabrice, are you with us? You made the experiments in the past on similar devices. In terms of long lasting experiments, how long was it? How much time does it last the experiments? In Florida, they sustain voltage and current during long. Very long. For a month. Yes. 1 month. Many months. I don't know exactly, but many months. This is an important information.